Hi everyone. In this talk, I will introduce DPCM, a paradigm that reduces data access latency through the control plane acceleration. This is the joint work between UCLA and Purdue. We all want always-on, low-latency mobile network services. When we access the mobile internet, we want to access it immediately. As we move around, we want the network service to be disrupted as minimal as possible. This demand will be more pressing in the future 5G because we have seen a lot of delay-sensitive applications, such as the VR and AR, the UAVs, the safe self-driving cars, the high-speed mobility on the trains, to name a few. To meet these stringent latency demands, there have been a lot of exciting research and industry efforts, such as the application of transport layer optimizations or new wireless technologies for better quality and speed, like we have seen in this morning's paper sessions. However, even if I have very good wireless network conditions and my application works well, sometimes I may still suffer from a long network latency. Why would this happen? It turns out that these are not the only sources of network latency. In this talk, I will present a new dimension that has been largely overlooked by the previous research. I will show that the control plane also plays a very important role to data access latency, which complements all the existing efforts. So let's first look at how control plane works in the mobile network. We use 4G LTE as one example. Today, the 4G LTE is the largest wireless infrastructure that offers anywhere, anytime mobile internet services. It's distributed in nature and involves wireless network nodes, such as base stations, gateways for data forwarding, mobility controllers, and user profile servers. Similar to the internet, the control plane defines a set of functions to facilitate the data delivery. To access the internet, the control plane should first establish a data session to the external internet. As your mobile device moves, you should migrate your session so that you can resume the data service. Before these control plane operations are completed, your data access will be blocked. That's why the control plane will have extra latencies on data access. Unfortunately, we find that control plane is really slow in today's network. We have conducted a 19-month user study over 4 US network operators and analyzed 95,000 of session establishment and migration scenarios. We have made 3 observations. First, the control plane latency is long. For all the network operators, every session establishment will cost 160 milliseconds, and every session migration in device mobility will cost 1 second latency on average. Second, such control plane latency have frequent impact on data latency because the session establishment and the migration are very common. We find that on average, the session establishment happens every 100 seconds because of its on and off radio connectivity characteristics. In your working scenarios, the session migration would happen every 17 seconds. Last but not least, transient failures exist in the mobile network, such as external radio link failures and internal control and data plane failures. Although they are not popular, they will incur significant latency once it will happen. We found that on average, it will cost 3 seconds actual latencies and can be up to 11 seconds. So why is this so slow? It turns out that the cause is a sequential execution of the control plane procedures, which is mandatory in not only current 4G LTE, but also in many ongoing 5G proposals. To correctly forward the data, the control plane should run a series of control functions, such as radio connected setup, QoS and data billing configurations, security and authentications, routing path update, and device location update tracking. These control procedures span on both mobile device and network nodes. To function correctly, these network nodes should have some consistent views of these control procedures. So in today's 4G LTE and many 5G proposals, they mandate the sequential execution of these control procedures. Of course, this is very intuitive and reasonable, but this is at the cost of long latency. Before all the control procedures are completed, you cannot send or receive data. So we basically ask, is it really necessary for us to retain the sequential executions? We find that the answer is no. without violating the correct data forwarding, we can relax the strict ordering of the sequential executions for 3 reasons. First, we find that some control procedures are not mandatory for data forwarding. For example, there's one control procedure between mobility controllers and user profile database which synchronize your device locations. However, none of them reside on a data path, so they are not directly responsible for data forwarding. Second, we find that some control procedures could run in parallel, but they are forced to run sequentially. For example, in updating a routing path, the mobility controller sequentially notifies the base stations and gateways. However, you could run them in parallel and save latency. Last, once the failure happens, any failure of single control procedure will block the entire sequential executions, which will further prolong the latencies. So motivated by this, we designed DPCM, a paradigm that reduces data access latency through control plane accelerations. Here's a quick overview. The high-level idea is very intuitive. To reduce the control plane latency, we relax the strict ordering of sequential control plane executions. We explore 3 dimensions. First, we bypass the slow control procedures and replace them with faster ones. Second, we pipeline data forwarding with control procedures. And last, we parallelize multiple control procedures. However, these are not that easy. We basically face 2 very fundamental challenges. First, how can we retain the control and data plane correctness? Relaxing the ordering of sequential executions is at the risk of incorrect control and data forwarding functions. For example, we may forward the data to the wrong locations, we may overbill or underbill data volumes, or we may even allow the unauthorized device to grant network access, right? The bottom line here is that any acceleration should retain the same functionality as the current 4G LTE without violating any correctness. Second, how can we achieve these accelerations efficiently? After many years of design and operations, the control plane has been quite matured. Is there any new opportunity for us to further accelerate it? To address these 2 challenges, DPCM explores 2 ideas. First, to guarantee the correctness, DPCM adopts ideas from distributed computing community's ideas. We reformulate the control plane acceleration as a state management problems and apply distributed consensus to guarantee the correctness. Second, DPCM explores a new dimension for the control plane acceleration that is called the control state replicas, which has been underutilized in today's network. With this feature, we can achieve shorter side passes, install states faster, and enable concurrent state operations. In the following, I will show how this will work. Let's first look at how we can reformulate the acceleration as distributed state management problems. To forward the data correctly, the mobile network requires the multiple control plane states, such as the device locations, QoS configurations, building policies, radio access control lists, IP address, and security keys and contexts. These states are replicated and shared by the mobile device and multiple network nodes. You can think of these control procedures as a series of state operations between these nodes, such as state creation, copy, updates, and deletion. Fundamentally, the core task of the control plane is to correctly install these necessary states on the specific corresponding nodes and ensure the consistency of the states between different nodes. To guarantee this, 4G's choice is to run this control procedure sequentially, but for us, we can think of acceleration as to figure out an equivalent but faster state operations. So that's how we do it. Then, in achieving this, the key observation here is that we have more than one copy of the control states. In particular, once the mobile device registers to the network, it already maintains the copies to function correctly. These copies is almost always on unless your mobile device leaves the radio coverage or explicitly registers from the mobile network. On the network side, you also have multiple copies on the base stations and on the gateways. In the current 4G LTE, it only leverages the primary copy from mobility controllers, but instead, DPCM uses all the state copies to accelerate the control plane procedures. So then, let's look at how we can do it. We'll see how to use it to achieve bypassing, pipelining, and parallelization. We'll first focus on the conflict-free case, and then handle the conflicts in the end of the presentation. First, DPCM will bypass the slow control procedures. This is equivalent to installing the states faster, right? So installing the same states faster. How can we do it? So our idea is to leverage the device-side state replicas. We piggyback these control states with the radio-connected setup procedure, so that once the radio-connected setup is finished, the base station can already get the states. This reduces the unnecessary control procedures for the state copy between the mobility controller and other network nodes. But we retain the same round trip as radio-connected setup. Second, DPCM will pipeline data forwarding with control procedures. As we said, data forwarding can start without waiting for all the control procedures. So the key here is that you need to install these necessary control states on the data path nodes so that they can start immediately without waiting for other control procedures. How can we do it? DPCM uses the idea of in-band signaling. We construct the IP packet and piggyback the device-side states with that IP packet. As this packet traverses data path, it can also install these states on data path nodes, such as the base stations and gateways. In this way, the data plane path nodes can start immediately without waiting for other control procedures. And the last thing DPCM does is to parallelize the control procedures. To do so, we can leverage multiple state replicas and enable the concurrent state operations. The issue here is that if we leverage the multiple replicas, we may have the risk of the conflicts. What if multiple network nodes update the state values in this process? How can we handle it? So to do so, DPCM's idea is to leverage the same premise as 4G LTE. We let the mobility controller to determine the final value. So more specifically, any network node with state replicas can propose its value to the mobility controller. The mobility controller can either accept this value or updates a unique new value through this broadcast message. In this way, we avoid potential conflicts. This is the basic idea of DPCM. And another advantage of DPCM is that these mechanisms inherently tolerate the failures using state replicas. For example, if the primary copy of the state from the mobility controller crashes, DPCM can still correctly install the states from other state replicas. So we can avoid the unnecessary blocking of the control procedures and reduce the latency penalty. In our paper, we have analyzed more cases of the failures, such as external radio link failures and internal control and data plane failures. For more details, please read our papers. So far, we have focused on the conflict-free case. What if multiple network nodes really update the states concurrently? This may violate the correctness of the data forwarding, right? The good news here is that we found this is not common. Our user study shows that all the state updates is not common. Only 1.3% of the state operations belong to the state updates or state writes categories. So usually this won't happen. But if it happens, how can we retain the correctness when it occurs? So in this case, the goal of DPCM is to retain the same functionality as 4G LTE and retain no longer latency than the 4G LTE network. The high-level solution is that we let the mobility controller to modify the state value only. Any local modifications from other network nodes are not allowed. This basically nails down to two scenarios. First, if the mobile device modifies this state values, for example, a selfish user may elevate its QoS to try to get some higher QoS. In this case, DPCM will detect these local modifications and roll back to 4G. To do so, it distributes a fingerprint together with state replicas to the mobile device. Once the mobile device carries these states here, it should also carry the signature, so that the network nodes can recalculate the signature and find a mismatch. Then, in this case, it will roll back to the 4G LTE with the same functionality and same latency. The second case is that multiple network nodes may concurrently update the values. In this case, as we said, the mobility controller can determine the final value, so that in this case, we have the we can retain the correctness. So we have implemented DPCM as an extension of Open Air interface, which is a software-defined control and data plane LT protocol stack. We have released our alpha version on our website, and the full version will be released soon. So our implementation supports incremental deployability and backward compatibility over existing 4G LTE network and commodity phones. To do so, on the network side, we implement DPCM as a shame layer between the existing 4G LTE stack and the underlying physical servers, without changing the LTE protocol stacks. And on the mobile device side, we can upgrade the mobile device using this software firmware update. So we have deployed our implementation in a local testbed and evaluated. So to approximate the real network, we configure our testbed using the real parameters, latencies, and failures from our user study logs. So now I will summarize our evaluations in 3 aspects. Its effectiveness in reduce the control plane latency, its benefits for the applications, and its system overhead. So DPCM can significantly reduce the control plane latencies in both static and mobile scenarios. Compared with the latency 4G LTE, DPCM can reduce the static latency from 160 millisecond to 80 millisecond, and reduce the latency from, in the mobile case, it reduced latency from 1 second to 170 millisecond. Note that in the mobility case, we have more latency reductions because the mobile scenario involves more control plane procedures, and so we have more opportunities for the latency reductions. So far, DPCM's latency is very close to the video connective setup latency, which is almost a lower bound. We also conduct a projection-based emulation to see if we can significantly reduce the 5G video latency. What would be the benefit of this DPCM? So we assume the 1 millisecond radio latency and run our evaluations. We find in this case, DPCM's latency reduction is more significant because if radio latency is already 1 millisecond, now the control plane latency will dominate. In this case, DPCM can achieve 1 order or even 2 orders of magnitude latency reductions. And lastly, when failure happens, DPCM will reduce more latencies, up to 11 seconds. DPCM's control plane latency, DPCM can also benefit the applications by reducing control plane latencies. We have tested YouTube video and web loading and find it can achieve tens of seconds of the latency reductions. Note that the latency reduction from the application is longer than the control plane latency reductions because the application usually will have some imperfect adaptations out and it will experience longer latencies. In achieving this, DPCM retains very marginal overhead. Its signal overhead is very marginal, roughly 50 bytes per message, and its CPU and memory are also marginal on both mobile device and network side. Before we conclude the talk, I would like to highlight one more thing. Fundamentally, our solution can be viewed as an initial attempt to balance the latency and consistency. In the distributed computing community, people have done similar things for years, but we demonstrate that this problem also exists in mobile network, and we also have a fundamental theoretical limit that is called CAP theorems. No mobile network design can achieve both sequential consistency, availability for low latency, and control plane fault tolerance simultaneously. This is a theory result. You can check the proof in our papers. In all the current existing designs, ranging from 2G to 4G network, they usually prefer the sequential latency over the other 2 properties. But we believe that it is now time for us to rethink the balance between consistency, latency, and fault tolerance. So in conclusion, we have 3 takeaways. First, we show that it is equally important to improve the control plane for low data access latency. This issue has been largely overlooked by the research community, and it turns out to be increasingly important. DPCM is our first attempt to do it. We leverage state replicas to achieve the bypassing, pipelining, and the parallelization with the fault tolerance way. And we believe in the broader context that more research efforts is really needed to rethink the latency and the sequentiality of consistency balance. That's all. So I would like to take your questions. Thank you.
Thanks, speakers.